Okay, welcome to another week of deep learning. This is, I think, the week number 8 of the semester. And today's topic is wrapping up the regularization of deep networks. And we have finished, I think, something like, this is chapter 7, 7.1 through 7.13 we have finished. Various methods of regularization we have covered, starting from norm penalty regularization, going all the way to dropout regularization. And the theme all along is regularization is to make the system generalize better to inputs it has not seen. We have not anticipated everything, but we've given you a training set, you learn, but not only that, you have to perform well on things you have not seen. That is the problem of regularization. So these last two topics that we're going to discuss today, one is called adversarial training, and the other one is relating to tangents of manifolds. Both are really intriguing topics. So these are getting into some research topics here, and they are just about this topic of regularization. Adversarial training is, okay, you want your system to do well on things it has not seen. And what are the kinds of things it has not seen, but it can make it fail? So is it possible to create examples that somehow will make the system fail, although you've trained on the samples you've got? So adversarial training is exactly that. How do I become an adversary to the training? So this is like a teacher telling the student and posing questions that are really hard for the student, and to make the student stronger, saying, okay, I never learned that, but I can now somehow go beyond what I learned, and try to do this new types of inputs, do well on these new types of inputs. That's adversarial training. There's an intriguing problem where we will see that taking the input samples and somehow manipulating in some ways can create some certain adversarial samples, and a system that is doing exceedingly well on the regular training data and also on the testing data that was generated, in a similar way, it does terribly on these adversarial samples. The performance goes from 99% accuracy to 1% accuracy. It is possible to construct such examples that the system totally fails on the system. So how does one construct those kinds of examples? Those are not, and these examples, if you look at these adversarial samples, they don't look any different to a human eye. You look at it saying, that looks like the 7 that you had there. It looks like a 7. Or that looks like the cat image you had. This looks like a cat to the human eye. But to the computer, it's totally wrong. It was getting cat as 99%. Now it is saying, this is not a cat or a dog. It's something totally different. It's a fish. Totally wrong answer. So it is possible to do that with this adversarial training. We look at that part and how to do that. We have to look at the mathematics of adversarial training, which involves starting with the sample and computing some derivatives and so on. The other topic we look at this is the tangents of manifolds. And manifolds are where data lies. So we argue that the data of a set of samples in this feature space don't lie all over the space. If you have a million pixel space, that is million dimensions you have along each, of which it takes 0 to 255, 8 bits per pixel. These images that you have don't spread out evenly all over the space. They are kind of concentrated on extremely small regions of that space. We refer to them as manifolds. We refer to them manifold because it is some kind of a surface in this space. All the data lies as points along this manifold. And when you change the data a little bit, it is moving along this manifold. It might be a complex manifold. It might turn on itself and come back and so on. So it can be a Klein bottle or what have you. These are called, manifolds. And so data lie on these manifolds. And then we say, oh, if that's the case, then there is something to be gained by drawing tangents at any given data point. So here is a surface and there is a data point here. If you draw a tangent in a three-dimensional space, that's going to be a plane here. When you draw a plane, which is a tangent, just like a line is a tangent, all right? And a linear object, which is a tangent, which is a plane. And we say, look, if you're going to be interested in knowing something about the manifold, we know the direction of the manifold. And so we can use that to take, let's say we are trying to implement a simple classifier called a nearest neighbor classifier, which simply says take the input and compare it against each of the samples and assign it to that sample which is nearest in terms of some distance. You could also say measure the distance to the plane, but if I do a tangent, it gives you some sense of how the object is varying. It's looking at a little more than a point, it is looking at the surface. And so that is useful to have a better method, which is somewhat invariant to the kind of transformation that led the points to move around on that plane. So that's called the tangent distance classifier. And then there is also a method called tangent propagation. In tangent propagation, it is equivalent, we'll see, to adding an additional penalty term to the loss function. So when we try to minimize the loss function, you recall that the norm penalty method was to have an additional term added on, which usually involved the length of the weight vector. Just like that, we can have something to do with the surface, which involves the tangent. Tangent is the same idea as slope. Tangent, slope, or dy by dx, or derivative. These all are related terms. So we bring that into play. And so here are some, now this all sounds like a pure mathematical play. Well, you're just going to be computing all these derivatives and making the classifier more complicated. But think about the bigger picture. We are trying to make the system generalize, or the neural network generalize to things that it has not seen. And also we can argue against those people who say, well, we are going to be limited by your data set, isn't it? AI is not going to be any better than the data that you present to it. That's the argument given by the people who argue against AI replacing general intelligence, right? So we say, look, we need to counter that. How can we start looking at those kinds of problems of becoming generally intelligent? So which is go beyond what you have seen and not simply based on the weight vectors norm, not simply based on adding noise to the data, not simply removing connections like we do in Dropout, but actually looking at the nature of how data varies and taking advantage of that. So it's got some good philosophical implications. And like many of the topics that I'm discussing here, each of these topics are rich enough to lend itself to a master's project. Some of you are all eager to do master's projects. And you could take on a small topic, such as I will study the tangent propagation method of regularization and see what does it take. Or I'll study adversarial training and say, what does it take to fool an AI system trained on a certain data set? So these are the kinds of questions. So my lecture slides hopefully will motivate you to pick up one of these as a possible topic rather than simply an end-to-end solution to some problem. All right, you built a system, but how brittle is it? Brittle means give it something that is not like that, and it shouldn't go bonkers, right? It should not say I cannot do it, right? So these are all ideas for those of you who are inclined towards deep learning research. So fundamental problems to be tackled than simply focusing on system building. Okay, I'm going to share my slides. We begin with adversarial training. Okay, there we have it. Hopefully you can see it. If you have any questions, comments, I welcome them. Put them in your chat box, or you can speak up. If you put it in a chat box, then Mohammed can actually read them out to me, because on my laptop, I just see the PowerPoint and I see a small list of the people who are in the class. Okay, so do ask your questions as we move along. Okay, now the topic again is adversarial training. This is topic number 7.14 in the regularization chapter of deep learning. All right. So the first slide here is a motivator. So what is the level of understanding of a deep learner? So we say deep learning networks can reach human level performance on an independent, identically distributed test set. But have they reached human level understanding? What we're saying is, given a set of photographs of cats and dogs or whatever, buses and cars, you ask human beings to ask what they are, they say what they are, and then you get the computer or your deep neural network to ask what they are. It says exactly, or even maybe better than the human being. But then the question we ask is, do they have a human level understanding of what they're saying? So one way to probe this is the second bullet point. It says to probe this, consider misclassified examples. And we say even networks at human level accuracy have a 100% error rate on examples intentionally constructed. So even if you have built such a good system, which is what your project is about, right? I'm getting 98% or whatever, you're going to come and tell me how great your project has been. Uh, should I be impressed? I'll say, look, I could easily construct examples it's going to fail on. So is it something you can pay attention to? So what are those kinds of examples that it's going to fail on? These are called adversarial examples. So machine learning models consistently misclassify adversarial examples. And what are these adversarial examples? Inputs formed by applying small but intentionally worst case perturbations to examples from the data set. So it involves perturbing the data set. And the perturbed input results in incorrect answer with great confidence. So that is this topic here. So look at these. This was, Karpathy, he's the guy at Tesla, the AI chief at Tesla. He wrote a paper quite some time ago, 5 years ago. And he showed this in his, I think this is a blog of his on GitHub. And he said, take a correctly classified. So these are all correctly classified from, I think, CFAR or one of those data sets. This is, a correctly classified as a truck or something. And this is correctly classified as a bird on the grass. And this is correctly classified as a South Indian temple over here. And you can cleverly modify this image from what is shown on the left to the right. To the human eye, you can't tell the difference between this school bus here on the left and this school bus here on the right, or this bird on the left, the bird on the right, and the temple on the left and the temple on the right. Only difference is there was some image here called the distortion image was added to this original image. This distortion image was added, distortion image was added. So pixel values all got changed a bit, not perceptible. And they ran it through the same classifier, which correctly classified them. It started saying all of these are ostrich, totally nonsensical. Similarly, we have one over here, and I don't know what it is, some kind of electronics or switches or plugs or whatever. And then here is, looks like a locust or a grasshopper or something. And here is a dog. And you add these kinds of, look at this generation. This noise looks like it's related to the original image that's been added specifically. X has become an X prime after you add this to it. And this is the X prime on the right side. To the human eye, there is no difference, but it's all become. So it was take a correctly classified image, left image in both columns, and add a tiny distortion in the middle column to fool the convolutional net with the resulting image on the right. Wow, we're in serious problem with convolutional neural networks. Oh, some more examples. There were some of these noises here that was added, and an image like this was called like king penguin or a starfish. Oh, originally, yeah, robin, something was added to it. This noise was added. Okay, I guess this noise was added like this, and then this noise was added like this. These images are classified with greater than 99.6% as shown by the as the shown class by convolutional neural network. Oh, okay. It said this is a robin, this is a cheetah. This is just that was input. This was input. It said that's a robin. This was input. It said cheetah. It was this input. It said armadillo, as a lesser panda. This is a king penguin, and that's a starfish, and blah blah. So totally wrong classifications, because these were very specifically generated, and these are what are called as adversarial examples. All right. So what is the cause of these adversarial example? What is happening? And Goodfellow wrote a paper about 5 years ago on this, where he said the cause of the existence of adversarial examples is excessive linearity. So you see, we always talk about linear models in neural networks. In machine learning itself, we talk about linear regression, linear classification, linear discriminant functions. And we go to neural networks also, we say here are linear, W transpose X is what? It's computing a linear function of the X. I'm multiplying by a set of values, add it up. It's a linear function. Of course, nonlinearity comes in when we input to the W transpose X to a nonlinear activation function such as sigmoid or ReLU, and we bring in some nonlinearity from one layer to the next layer. But basically at each layer, it's linear functions. At the next layer also, we take all these outputs of the sigmoids, again, make a linear combination, so on. So the overall function often proves to be linear, the linear building blocks. Well, why do we do that? Is linear functions are easy to optimize. So we do derivatives of linear and so on. The derivatives of those linear activation functions are extremely simple. Derivative of sigmoid is a very simple form involving sigmoids. The derivative of ReLU, do you remember what the derivative of ReLU is? ReLU is of the form 0 and then X, right? That's how it looks like, the ReLU activation function. And what is dy by dx when y is equal to x, right? Right? What is dy by dx when y is equal to x? It is actually equal to 1, right? So the derivative of x with respect to x is exactly equal to 1. So that's a very simple thing to calculate, derivative for a ReLU function, even simpler than for a sigmoid computing the derivatives. So when you go back propagate, you need to be computing derivatives, and you will be computing derivatives of, and then replacing the values by the derivatives at that point, then they're simple to compute, and we back propagate them. And of course, we are back propagating the loss. And so these optimizations become fairly straightforward. Our next chapter is optimization. So there are many optimization methods also. But the value of a linear function can change with numerous inputs, okay? Can change rapidly with numerous inputs. If we change input by epsilon, then a linear function with weights W can change by epsilon times the norm of W, which can be very large in high dimensional spaces. So the norm of the vector, although we're trying to keep it short, it can still be quite large. So if we change the input by a small amount, then if you think of some linearity, if W is very large, think of it as a linear function. W is the weight vector. So the amount you can change by epsilon times W itself can be very large. So we're going to explore more generating adversarial examples. An optimization procedure is used to search an input X prime near a data point X. So we have a data point X here. This is an actual school bus, such that the model output is very different. So we're looking for a slight modification of the school bus, and the output is going to be very different. In many cases, X prime can be so similar to X that a human observer cannot tell the difference between the original example and the adversarial example. We just saw that. We could not tell the difference between those. But the network makes a highly different prediction, which we also saw that it's possible. So how do we generate? So we now get into how do we challenge our neural network, which is exactly what regularization is about. We want it to perform well on things that it has not seen, and how do we challenge it? So deep learning researchers have come up with several methods. A simple one is called fast gradient sine method, FGSM. And that's what we'll talk about today. I won't go over every one of these methods. There is something called basic iterative method, BIM, or a projected gradient descent method, PGD. So there are all these approaches which are simply seeing what can we do to fool the classifier so it can do better. This is what the FGSM adversarial example generator looks like. So here is X. X is this image of this panda. It's an RGB color image. And the particular classifier that was trained, it says, okay, the Y is the output for this input X. It says it's a panda. How sure it is? It says 58% confidence. It depends on how many other classes there was. 58% is more than 50%. So I guess that would be the best choice. Okay, that's a panda. All right, we'll say, great, your classifier does well. But I'm going to add to X an imperceptibly small vector. Its elements are equal to the sine of the elements of the gradient of the cost function with respect to the input, right? So there's a cost function associated. So when we go forward, we can calculate J of, depends on the weight vector you have, right? So we have a cost function J of, which is a function of theta, the parameters, of X, the input, and of Y, the output. And it's a certain value, which we have, of course, tried to minimize overall, but for any given input, you can compute that value. So, so we take the derivative of the loss function, which is, this is the nabla symbol, which is the derivative. This is the gradient of a vector here. And with respect to X of J theta XY, it is the value of the derivative of the cost function. And this is a function called sine function. It's a very trivial function. Sine function takes a number as input. And if the number you give it as input is positive, it will say +1 is the output. If you give it a negative number as input, -1 is its output. All right, so it just knows, I guess 0, it's going to be 0. So if you give it a positive, so it says this function sine of the derivative of, so you see derivative can be positive or negative depending upon the derivative. We're calculating the derivative in the maximum derivative direction. In that direction, it can be positive or negative. And so it is determining the sign of that. And that simple sign, which is +1 or -1 or 0, is being multiplied by a small quantity 0.007. And that creates this image, which is written here as X plus epsilon is this quantity, 0.007, sine of the derivative. That is this image. All right. Here is an interesting point. If you input this image into that same classifier and ask it, oh, what do you think this is? It says Y is equal to nematode. I suppose there are so many classes there. And it was totally confused. With a low confidence, it says, well, the best I can think is a nematode. It is not even any kind of, it's probably one of the rare animals or whatever this nematode is. And then when you added this noise to this, it says Y equal to gibbon. Gibbon is kind of a monkey, I think. And it's saying that's a gibbon with 99% confidence. Totally messed up its performance. You're talking about supervised learning here. You trained it on pandas and nematodes and gibbons and so on. And you say, look, I did well on the test set and so on. Here it is. It's extremely highly performing classifier, and you now give it one example like this, it's totally gone bonkers. All right. So let's talk about, this slide is trying to tell us about, I'm having some trouble arranging stuff on my laptop screen. Okay, there we are. Let's first talk about precision of an input feature. Supposing those images we had 8-bit resolution. That is it. There's a million pixels, and every pixel is allotted 8 bits by the computer we're using, by the GPU. 8 bits is a very good resolution, which gives it 255 values for one color, actually. And then you would repeat it RGB, it would be 3 times that. That is how many bits are available to encode one little point on the image. But we discard information below epsilon equal to 1 over 255. 8 bits gives you 256 values, 0 to 255. And if there is a fine variation, even less than that in terms of the resolution, then we say, look, we cannot tell because we're representing it with only 8 bits. So we say there is some epsilon there below which it's too small. And let's say we need the same response for x and an adversarial version of x, which is x tilde with this symbol on top. It's called x tilde, which is nothing but x plus eta, some other eta here, some Greek symbol eta, for small elements of eta. That is, this is called the norm of eta. And we say when you put an infinity below, it's called the L infinity norm. And L infinity norm is like L1 norm, we know that, right? L1, L2 norm, we know about that. But what is L infinity norm? It's called the max norm. Max norm means if I give you a vector and the max norm is simply the maximum value in that vector, right? So that's called the max norm. So whatever that value is, that is the max value. And we're saying if the maximum value of what you're going to be adding is kept less than epsilon, right? Say such a small quantity. And we are making sure that the quantity you are adding here along every dimension, this is a vector here, right? X tilde x. So every one of them is going to be less than epsilon. Then we need the same response for x and x tilde. All right, so then let's consider the activation W transpose X tilde. So we are now going to be dealing with not just W transpose X, but W transpose X tilde. So that can be written as W transpose X plus eta. We substituted X tilde equal to X plus eta. Or it can be expanded out as W transpose X plus W transpose eta. So what we are doing is we are adding something to this linear quantity here, W transpose X, we have another linear quantity involving W transpose and some value here, the noise we're adding, some small noise we're adding. So adversarial perturbation grows it by, so the perturbation is the input to the activation function, it is growing by this amount, W transpose. So we maximize the increase of this output by assigning eta equal to sine of W. Sine is defined as I told you earlier on. Sine function is -1 if x is negative, 0 if x is 0, and 1 plus 1 if x is greater than 0. Unfortunately, my slide has cut off this bottom portion. I didn't realize it until now. It should, when I converted the PowerPoint to the PDF, I think it cut it off here. So, okay, the arguments here, if I try to recall, okay. Okay, all right, my original slide also doesn't have it. Okay, so here let me just generally say it. Oh, okay, there's something more here we can say. For n features, activation growth. I see. Okay, now I recall. Supposing there are n features we're dealing with, this X is n dimensional, and the average value of this vector over an average over all the samples is equal to m. The activation growth, when you change the input, by adding an eta to the input, the growth of the activation is going to be W transpose eta, which is what we saw here, and that's going to be equal to epsilon times m times n. This comes out of the fact that it's not more than epsilon. Maximize the increase, epsilon. M is the average length of the vector. N is the number of features. Okay, it sounds like a small quantity, epsilon. What is the average value of the W? And what is the, so that is the quantity we're increasing this by. And this can be a large amount is the argument. When N is large, when you have a large number of features like we have in these images, this quantity we're adding, even though we started out with a very, very small quantity, you are dramatically changing what's going into the activation function. And if we're dealing with ReLU or something like that, it can have a dramatically changed value, because ReLU, as you recall, output is the same as the input for positive values, right? And so if this is going to be a very large value, that's going to go and change that. So that is what is happening. This was an argument here. This slide was an argument here to show why a small change in the input can make a big change in the sigmoid function or the activation function we are using. Okay. All right, linear perturbation of nonlinear models. So, of course, the entire networks are nonlinear. The individual layers are linear. Linear view of adversarial examples suggests a fast way of generating them. Right? They can be done fast. LSTM, ReLU, and max out nets. Right? Max out is another kind of activation function. Just like we have ReLU and sigmoid and so on. Max out is a one more sophisticated method of activation function. Our ReLU is also an activation function, are designed to behave in linear ways for easier optimization. More nonlinear models, such as sigmoid networks, are tuned to spend most of their time in the non-saturating, more linear regime for the same reason. When we're dealing with sigmoid networks, if you are on the top and the bottom, if it is at the 1 level or the 0 level, there is no gradient value there. So we kind of try and drive them towards where there is some gradient value, which is not 0 or 1, not saturated, we say. And so these are some facts that we use to generate cheap analytical perturbations of linear model that should also damage the neural network. So it is possible to generate in a cheap way these kinds of samples. So we want to generate those kinds of samples. Of course, if it is impossible to generate it computationally, is no good. So it can be done. All right, so that is the method of fast gradient sine method. It involves the gradient shown here as delta or nabla, which is the gradient of J, which you saw earlier on. That's called gradient. Sine, it uses a sine function. And we say it's fast. The reason we say it's fast is the required gradient can be computed fast using backprop. Backpropagation is the standard method of generating gradients, and that can be done fast. That's why it's called fast gradient sine method of generating adversarial examples. And the eta you're going to be adding is exactly this, some epsilon times this. That's what gets added, to X. So X becomes X tilde by adding this to X. So adversarial training of logistic regression. So this was an example. Okay, let's see. We talked about adversarial example for neural networks. How about for a logistic regression, which is the very simple primitive form of neural network, where we have W transpose X transformed
Professor?
by a sigmoid function to produce a value 0 or 1, right?
Professor, there is a question.
Yeah, go ahead.
Okay, so the question is that can we create inputs using an adversary, then assign it original class and include it in the training data set?
Yeah. So that is the conclusion we are going to be getting is create. So this is just like another topic we saw in regularization, which was called augmented data sets, augmented, right? What do we do in augmented data sets? Take the inputs, add noise to it, or distort it, and enhance your data set. So that is exactly the way of augmented data sets. So this is saying, this is one way to create it. Take those samples, but then you're going to be facing this challenge of how many of those to add and how many times over is your data set going to be. So there are all kinds of issues here. But sure, that is a method of doing it. But are there cleverer ways of doing it is the question. All right, let's see if there are any answers to that. But that's exactly the way that it is suggesting itself to do, is to train it with adversarial examples. Okay, let's continue. So fast gradient method is exact for a, it turns out that when you say exact, that is the worst case scenario for a logistic regression, to use that gradient as we talked about. It is, you cannot do any worse than that. Most damaging example in max norm box, in max norm they're using here as the activation. Okay, weights of logistic regression model. So they're showing a picture of what the weights of the logistic regression model looks like. So, you can think of every pixel here as a weight. So we are using this for the problem of MNIST, which is a handwritten digit recognition, 0 through 9. And so we are multiplying each pixel value, like the 7, right? That's a pixel image of a 7. Each pixel is going to be multiplied by the value shown here. It's some value between 0 and 1, it looks like, if it's grayscale, or 0 to 255, yeah. And they're also calculating the sign of the weights of the logistic regression model here. Okay, just a sign, positive, negative, or 0. It is showing over here. These are the actual original MNIST images, and they're only showing 3s and 7s here, 3 and 7 images. So they said, let's train a 2-class classifier for 3 images and 7 images. Let's see how well it does. Logistic regression has an error rate of 1.6% in 3 versus 7. So they trained it on this image set, and it figured out all these weights, and it does a great job, 98.4% accuracy. Well, what they did here was they created these adversarial examples. So these are the examples. I guess there's the individual images. These images all got corrupted by the noise added to them. And then they trained it on the original logistic regression method. It has an error rate of 99% in 3 versus 7. These don't look so much like 3s and 7s anymore, but it's interesting, right? And those images of buses and animals, they look pretty good. But these, I think they're such small images. There is a sense of what they were, but they're somewhat distorted. Anyway, so this can be created. So the main point here was you can create such images that are pretty bad. And they were using epsilon equal to 0.25 for this. So of course, what we could do is, well, we could add these to the training set. That was the question, right? Or we can change epsilon equal to something, add those to the training set, and so on. So where do we stop? So that's one of the things. So this is a bit more detail of the logistic regression Fgsm. Now we are saying we can somehow construct a different model which has got a different way of regularization. So this is a logistic regression which is regularized. So trained to recognize y equal to -1 plus 1. So this is not a 0-1 classifier. With p of y equal to 1 is sigmoid of this. So the inputs have labels -1 or +1. Okay, 2-class classifier. Okay, it should say -1 or +1. The output of the sigmoid or the of tan h is going to be -1 or +1, but the inputs are maybe 3 or 7, right? X is the image of 3 or 7, and y is just one of the two values. The training consists of gradient descent on expected value of x. Expected value just simply means summation and average value. over the data set, XY pairs. They're using here the soft plus activation. What is this soft plus? Okay, remind yourself, soft plus is this, I put this picture over here. So soft plus is this green curve, which is quite close to the other one, which is in black, I think, which is the ReLU, right? So this is called soft plus function. And we train it, derivative of soft plus is sigmoid. This function is the close relative of sigmoid. And so training consists of this. The sign of the gradient is minus sine W. And so they're calculating the gradient here, and minus sine of W, sine of the gradient is this. And W transpose sine W, which is what we're going to be calculating, which is actually the L1 norm of W. Somehow L1 norm comes into play here. And so the adversarial version of logistic regression is therefore to minimize this quantity, which is again the sigmoid, or in this case sigmoid, it is the soft plus of minus y belongs to this L1 norm minus W transpose X minus B. So we say unlike, so this is summed over all the samples. I take the average over all this. So this is actually the loss function we're talking about. When we say minimize E, remember the loss function plays a role in in what we're trying to optimize, right? That we're trying to minimize that quantity. So this is the loss function. That's what we're going to do gradient descent on. And that loss function is now added this one term. And unlike L1 regularization, the L1 penalty is subtracted off the model's activation during training. So this is another variant of logistic regression where we are computing a loss function like this rather than the usual way. And it says, it turns out to have this nice form. So it is possible to add this as a regularizing term. L1 weight decay. So adversarial training of deep nets. Okay, you're not dealing with logistic regression, you're dealing with deep networks. Training on a mixture of adversarial and clean examples. This training is different from data augmentation. Usual augmentation is data with transformations that are expected to actually occur. So normal augmentation is you take the data, it's going to be rotated and so on. That's what our ordinary augmentation is. This form uses inputs unlikely to occur naturally. You're not going to be seeing these in the real world, but they expose flaws in the way that the model conceptualizes its decision function. And the adversarial objective function based on FSG, and we just saw what the adversarial objective function based on FSG is, right? So this says to be able to tune the classifier, the regularization you're doing is in this manner. And so it is different from the original manner. I wish there were some examples how well it did after that on these kinds of data sets, but I don't seem to have it readily available here. Hey, there's a nice project for you, is adversarial training, and how bad it gets and how much you can recover by doing adversarial training, okay? All right, now this is an important topic for a lot of people. Why would you want these things? Adversarial examples have many implications. Example, they're useful in computer security. Adversarial examples are hard to defend against. So if somebody knows that a neural network is operating your computer security system, I could break into it by sending it adversarial examples and break it, and it will say, okay, that's fine, I'll let you in. It's maybe that's what they're doing in all these. The Russians are attacking American systems or whoever, right? So it could be like this. They're also interesting in the context of regularization. Using adversarially perturbed samples, we can reduce error rate on the test set. All right, so you are now going to be more robust in your design of neural networks by knowing about adversarial. Adversarial training discourages highly sensitive local behavior by encouraging network to be locally constant in the neighborhood of the training data. This can be seen. So because you see, we are taking the individual data and then converting it. X is becoming X prime or X tilde. This can be seen as a way of explicitly introducing a local constancy prior into supervised neural network. This is all about supervised learning here, because we're talking about the classification, something to do with its being on the manifold and so on. Adversarial training and capacity. So adversarial training illustrates the power of using a large function family in combination with aggressive regularization. Right? So this shows the value, the importance of regularization. Purely linear models like logistic regression are unable to resist adversarial example because they are forced to be linear. Okay, so neural networks are able to represent functions that can range from nearly linear to nearly locally constant. All right, so thus can capture linear trends as well as learning to resist local perturbation. Okay, so this is just giving you some kind of intuitive explanation what's going on with this. All right, so we conclude this section by on adversarial training with a few other points. Relation to semi-supervised learning. What's that? We saw that earlier on. If you've forgotten what is semi-supervised learning, it's also, we said it's a method of regularization where we are saying we only have a few labeled samples and we have lots of unlabeled samples. So we say we can learn the distribution of X. X is the input. P of X, we can, it's available. We can figure out P of X, but we only have a limited number of data points, X comma Y. With X, there is every X, there is a Y. That's called supervised learning. Semi-supervised means tons of X. We have a nice distribution of X, but we have only smaller example of the joint distribution, P of X comma Y. So we say that combination of that pair of values, how many examples do you have? Well, very small handful. And so the problem like that, when you have P of X and P of the small of Px comma Y is a semi-supervised learning problem. So in semi-supervised problem, at a point X that is not associated with a label in the data set, the model itself assigns some label Y hat. We saw this earlier on. If your data set consists of so many peaks in the distribution, and we had a few samples associated with each peak, then they say, that whole Gaussian associated with that peak, maybe it can be labeled as whatever it was that one sample you have. So it assigns a label Y hat to all those data samples you have, which have not been labeled. May not be the true label, but your model is of high quality, that is the model you constructed saying, I have discovered 3 peaks in the data, then Y hat has a high probability of being the true label. So if you've got a very good model you have created of the data, it's possible to do well on semi-supervised learning. We can seek an adversarial example X prime that causes the classifier to output a label Y prime with Y prime not equal to Y hat. So it says an adversarial example that causes, let's say we have an example here that causes the classified output label Y prime. And we can say you can choose that Y hat to be the Y prime, all right? So it says this can be a technique that can go into semi-supervised learning, the same idea of adversarial. So you're generating new points, X prime, using the method we just described, and those can be used to assign to them, saying, okay, it should have the same, whatever you would have assigned to that Y hat, we are assigning to that Y prime that you've generated. So it's a way of generating samples or samples with labels. While I'm on the topic, I want to mention we have today a distinguished PhD student attending our class, Mihir. He decided to come today. Mihir is going to be presenting his dissertation proposal soon, and his dissertation has to do with self-supervised learning. And he explains very clearly that self-supervised learning is different from supervised learning. It is different from unsupervised learning. It is different from semi-supervised learning. And it is a case of unsupervised learning where it again creates a very good model of the data. And even without having any labeled samples, it goes about giving them some labels that turn out to be fairly good so that it can be useful. So self-supervised learning is that. It's even harder problem than supervised learning or semi-supervised learning. It's kind of an unsupervised learning problem, but it's intelligent unsupervised learning. Okay, I'll leave it later on to deal with that. We haven't talked about self-supervised learning. There is something else here while we are on adversarial examples. Adversarial examples generated with using not the true label, but a label provided by a trained model are called virtual adversarial examples. So these are, the classifier may then be trained to assign the same label x to x prime. We just saw that we could generate adversarial example, assign the same x and x prime, get the same label. This encourages the classifier to learn a function that is robust to small changes anywhere along the manifold where the unlabeled data lie. All right, so this says you can have virtual adversarial examples. These are not real examples, they're virtual examples, and they are generated by adversarial method. We saw how it could be generated using gradient and so on. And the assumption motivating this approach is that different classes lie on disconnected manifolds. We're saying the cats all lie on the cat manifold, the dogs lie on the dog manifold, the school buses lie on the school bus manifold, and so on. A small perturbation should not be able to jump from one class manifold to another class manifold. And so that is what is being used, saying a small jump will probably keep it on that manifold, all right? So anyway, that's a method of regularization I want to leave you with. So it is a very intriguing method of regularization. It shoots down your method very quickly. It's better to be aware of that than somebody trying to you know, to defeat you on your neural network. One last slide I have. I added this slide at the end. Adversarial. We've heard that term before. Where did I hear adversarial before? Well, you would have heard it not because of adversarial training. You would have heard it because you heard of generative adversarial networks, right? Again, these are very different things. You know, it's easy to confuse between the two. They are not one and the same. The goal of adversarial training is to develop better discriminative models, because we are still talking about neural networks to do classification, supervised learning type of problem. It could be semi-supervised, but still supervised learning problems. And we're saying, how can we regularize them better? How can we generalize them better? That's what adversarial training is about. On the other hand, what is this topic we haven't come to yet? Generative adversarial networks. They use the word generative. Generative means that is not a discriminative model. Discriminative model is to do classification or produce an output in regression, whereas a GAN is just to create a model which can be sampled to generate new samples from the network. All right, so to obtain a generative model. And it says, well, you know, how do you make a good generative model, not simply based on the samples you have. It should be able to be strong in terms of what kind of samples it generates. And the way they go about doing it is using a generative adversarial network. So it uses what's called as a generator network G, and it uses what's called as a discriminator network D. And using some noise, the generator network generates some samples. Of course, it's a model that is supposed to generate very good samples for every input. Noisy input, maybe coming from a Gaussian or something, it generates a sample. And we have real data here, X data, and this is X fake, we call it. This generative model is generating samples. There's a discriminator that is able to take either of these inputs and say, hey, that's a fake. Oh, that's a real one you've given me today. So on. So it is able to discriminate. And so this is going to be as good. So we need a generator that needs to be updated. And we need a discriminator that performs as well as possible. And when you say that it is wrong, Okay, you mistook a fake to be real, or you took a real to be fake. Then we say, well, we need to figure out the weights here in the discriminator. We know how to train discriminators, right? So that's something, and that's again backpropped on to the G here to be able to update its own method. So they get stronger and stronger. It's like two people having a uh, one of these. Fights we do with the arm wrestling, right? Arm wrestling. So I was saying we push from one side, we push from the other side, make it stronger and stronger. So they both get stronger. All right. So that's about adversarial training. Okay. So any other questions on this topic? We move on to tangent method of.
Professor, there is a question.
Yeah. Go ahead.
So, in the earlier slides, you displayed the images
Mhm.
on top of which you add some kind of a noise, and you create an adversarial example, uh,
Mhm. Yeah.
like 0. Yeah, something like that.
Mhm.
So, so there are two questions over here. The first question is, there is also a regularization method in which you add noise to the weight, right?
We saw that earlier on. Yeah. Noise.
Right.
Yeah.
Yeah, so first question is, so how is that different from this method?
There you're just adding noise to the weights, right?
Right.
And this is pretty serious stuff. We're just changing the input. Weights are things that you multiply the inputs by. And okay, that's the weights can be occurring in layer one, layer two, layer three, somewhere, maybe down the line. It doesn't make that much of a difference by adding a little noise at the weight at the way along. This is starting right in the input, which is going to be corrupting everything along the way. And such a carefully tailored thing that's screwing up everything, because that small epsilon you're changing is getting multiplied. We saw epsilon mn comes into play. How many samples there are, how many dimensions you're dealing with, that is coming into play. Epsilon times 1 million. So, and then what is the average value of the weight vector and so on. This can cause serious damage but just the weights coming later on, I would expect it doesn't cause as much damage. Hey, there's a nice idea for somebody who asked this question. That'd be lovely to, you're making a project to study a couple of methods of regularization. I will study what happens when you corrupt CFAR images with noise in the way. First, I'm going to train it a very nice classifier I'm going to get. Then I'm going to add noise to the weights and see what happens on the test set. And then what happens on, when you deal with these kinds of adversarial things. And this is to protect itself on these kinds of attacks, specifically make it to fail. You're not dealing with the real training data, real test data, creating adversarial examples.
Right.
Right. So you can see what are the relationship between the two. What is the
I mean,
relationship between? Okay. So anyway, that specific thing, how much it is, I'm giving you my intuition
okay.
that that's not as damaging. Okay. Tell me
And there
what is the next.
there is another question. The question is like, so this is kind of an adversarial using example generation using FGSM for images. So can is there a similar way to do it for sequential data?
Very good question. I don't know. See, you have to kind of now forward take this and see what are the papers that are dealing with. See, this was an original idea. It was 5 years ago, right? This Goodfellow paper came out in 20. This is from a Goodfellow paper of 2015. And people had observed already with images, it was possible to have adversarial examples. And so then they said, how do you generate these examples and so on? And from what I can tell, this there's always an analog in the language model case too. In language models, this is for the supervised learning problem. In language models, there are only small number of problems that are like supervised learning problems, like saying what language does it belong to, or you what sentiment is that a positive or a negative sentiment, or what kind of text is this? Is this sports, or is it politics, or what is this? So those are all classification type problems. A lot of language models with sequential data deal with machine translation, sequence to sequence type of problems. And so harder to characterize those kinds of problems. So I'm sure there is a whole parallel literature. And you see, I mentioned some more methods. I came across these. I was trying to say, what are the methods here? And I said, wow, there are all these methods. And I mentioned a few names, BIM and something else, right? So you may want to see what these are. And I had a slide earlier on here that even mentioned LSTM. Uh, and there might be some work on LSTMs and so on. LSTM sounds like they are behave in linear ways. So they're all subject to the same issue. And so there might be some studies available, and you could enlighten us. Which reminds me, I'm really looking forward to all your individual projects, which is why I'm making myself available every Thursday at 10 o'clock, 10 to 11, and I'll take as many I can. And please come there and say, oh, I've revised my idea. I'm going to do this project because this sounds like a real contribution that I could make. If you have a small paper talking about noise on the weights versus adversarial, that seems like it's worth a paper because nobody has made that study like that before. So on. And what about is FSGM useful for language, right? That's another small little study, right? These are all things that we could all use. Okay, any other questions? Okay, all right, let's move on to my other topic, which is equally interesting, I think, and equally complicated, or maybe slightly more complicated. And I'm going to close this guy here, and I will open another one, which is tangent distance, tangent prop, and manifold. This is the last topic in regularization. As you can see, regularization is a rich topic. There is a lot to be said here. And I'm going to go into slideshow mode. So this is labeled as tangent distance, tangent prop, and manifold tangent classifier. Tangent distance, I usually talk about it briefly, even in 574, the Introduction to Machine Learning course. I used to even talk about it in the early pattern recognition courses I used to teach, because that method is an old method that has existed. It was actually invented by a fellow called Patrice Simard, who used to be at Microsoft. And he came up with this idea that things that you train your network on, have to deal with the changes in the input. So if we have some examples of dogs, let's say, we have these examples of a certain type of dog, but then each dog can have so many variations of it, turning it left and right, and the picture is rotated around or scaled big and small, and you can create an infinite number of examples from one example. And how do we deal with this? As it is, the data set may be large and you're even scaling it up by so many more. And so how do we deal with it? So he suggested that we can work with the space in which the data is present, and we can somehow create tangents to that object on the manifold, and kind of get a sense for how the nearby points are. So tangent leads to how much of a change is present, right? That's what slope is. It is saying, how is the function changing? That's what it's measuring. And so he said, well, you take your data set and you create from it new samples, which are slightly different from it. And how different should it be? It should take into account a kind of a transformation, like a rotation, standard geometrical transformations, and work that into the kind of transformation it's going to have on your data. And so now, instead of measuring a distance from the original point from any given new point to the sample you have, let's say it's a nearest neighbor classifier, instead of measuring the distance to that point, we look at slightly modified version, which has incorporated its derivative into it. And we say, well, maybe that allows it to be more general than the original one. It is saying that is the kind of change it is tolerating. So instead of computing a simple distance to the manifold, we use the tangent at that point, and you compute the distance to the manifold instead of distance to the point. So it comes up with a fairly straightforward classifier where the distance you're using is to the tangent plane. That's the first method. So there are three things here going on: tangent distance. Tangent prop is a method of regularization, which is, let's take that idea of the tangent and create an additional term in the regularization term in the loss function. And we add one more term that somehow incorporates this tangent idea into it. Just like we saw for the adversarial, they're kind of related topics. The adversarial one also tried to do this as a regularization term. Tangent prop also does the same thing. And then there is another method which came after tangent distance and tangent prop called the manifold tangent classifier, which incorporates some of these ideas. And apparently it has been used in things like reinforcement learning. In the manifold tangent classifier, we allow for changes to take place on transformations that we don't know about. In tangent distance and tangent prop, we think of things like, what kind of transformation can there be? Well, the image can be rotated on the plane. The image can be scaled bigger or made smaller, or the images can be moved left to right or top to bottom. So those are all known geometric transformations in the plane. What about in 3 dimensions? It could rotate the object in 3D and you're looking at a 2D image. And there could be other transformations that the human eye, we didn't think of it. There are so many others. Maybe the tangent is with respect to movement, right? The zebra is moving along, so there is a change along motion here, and things are all changing. Or maybe talking about the zebra, the head is moving as it's moving along, the leg is moving this way and that way. So one part of the object is moving, left to right. The other one is moving, right to left or bottom to top. So the whole object is not moving the same way. It's got all these different motions happening at the same time. And how do we deal with that kind of thing? Tangent distance was, I know the kind of transformations you're going to be dealing with. And this is saying, oh, okay, so let us get away from predefining the kind of transformations that the data is going to be dealing with. It's got to figure it out, and it's got to be figuring it out with respect to different parts of it and so on. So this apparently has been used in areas such as reinforcement learning. Reinforcement learning is a popular topic in robotics, right? Where it has to learn on its own how to move around, like the Roomba, the vacuum cleaner, right? The vacuum cleaner runs around the house and picks up dirt. And Roomba figures out by running into the wall and running into the furniture that, oh, okay, I shouldn't go there. And it has not been, it is not supervised learning. We don't give it a map saying, okay, you clean the room in this way. Maybe some Roombas do that, I don't know. But the, less intelligent Roombas do it by just starting out and running into things and say, okay, it creates a mental map of how this room is. And so that's all reinforcement learning, saying, okay, so that one, if I go that way, it's going to run into a wall. That's a negative reinforcement. And I know if I go in that particular open path, that's positive reinforcement. I can keep going and going, so on. So there are all these things coming into play here. And how do we regularize our classifier to do things on all these kinds of dimensions? Again, a research topic. Some of these are hard problems. Tangent, distant, tangent have been around for, I would say they're this is about 30 years old. They've been around for 30 years. Manifold tangent classifier is a more recent topic. But anyway, let's look at them. Manifolds in data space are our first topic. The data exists in manifolds. How do you know that? Okay, we'll argue that. How do you define tangent distance? And then how do we define tangent, propagation, regularization? And then what is this manifold tangent classifier? And I just threw in one topic which doesn't really have to do with regularization here. It's called manifold learning. That is a big topic in machine learning. It's about representation learning. How do you figure out, what are the manifolds for each object? Manifolds is just a little, I've got a, I don't know if you can see it. I got a, coffee cup over here. That's a manifold. The surface of it is a manifold, not the inside of the, the porcelain or the inside of the material it's made of. That's not part of the manifold. Is the surface of the object. Data lies on the surface of the object. And so all the data with all, like one dog, right? We take a picture of a dog and we rotate it all over, move it around. It's going to move around on the surface of the object. And that whole thing is the manifold. So manifolds in data space. Data lies on low dimensional manifolds. Well, somebody laboriously tried to plot the manifold of handwritten digits in two-dimensional space. We're only measuring 2 dimensions. Maybe we mapped it using PCA from a high number of features, which could be all the pixels, down to 2 dimensions. And in PCA, we map it such that the variance is minimized and so on. Maybe we used a method that is going to make the within class scatter minimum and the between class scatter the maximum. It says the zeros are all over here in this 2-dimensional space. We plotted into 2 dimensions because that's all we can see. So, and then because originally it's in a very high dimensional space, we can't see what kind of manifolds there are. Look at this, zeros are all here, ones are all here, twos are here, threes are here, and then there is fours. Oh, look at that. 3 and 4 are different in this space, huh? I don't know why. Maybe 3 consists of several curves and this is like several straight lines, maybe. And here is 9s over here, and then 7s over here, and 8 over here. 8 is not too far from 6 here. That makes sense. There's some loopy thing here. 9 is a loopy thing. Maybe it's similar to 8 in some way. And 7 somehow hangs out by itself. 0 hangs out by itself. Close. I guess 6 is not too far from here. 1 is away and so on. All right. So these are the kinds of manifolds. But a manifold is a huge topic. I think there's a whole branch of mathematics called topology, right? There are whole professors and courses maybe on this topic, which I imagine is extremely complicated. And well, anyway, if you're a topologist, learning machine learning, this kind of stuff is great for you. So you common examples of manifold. Here is a sphere. Here is a torus, like a donut. You see, this one has a hole in it, right? It's a different topology. And here's a double torus, 2 holes. Here, I don't know what this is, crossed surface. Cross surface, looks strange, isn't it? It's somehow reattaching itself. I don't know how exactly it does that, but I can imagine what a Klein bottle is. You can go through it and you kind of can come out of it. It's a Klein bottle. These are all surfaces. You can actually have your data in the form of a Klein bottle. As let's say these zeros. We're saying that zeros form a Klein bottle in some high dimensional space, in this 3-dimensional space here. 6s form a sphere or whatever, right? These are all individual manifolds. They're all different manifolds. Note that the manifold is only the surface of these objects and not the interior of the objects, just the surface of these objects. So data lies on low dimensional manifold. It is saying, even though you've given me so many degrees of freedom, the data says it's going to rest on one manifold, which is what overcomes what's called as the curse of dimensionality. How could you solve a problem with 1 million dimensions? Say, look, the data just lies on a very low dimensional manifold. The 7s may all lie on a string, a 1-dimensional manifold. It's just small, so it's not in million dimensions. It's like 1 dimension or 2 dimensions or 3 dimensions and so on. So this slide is just giving an intuition of, and one more intuition of why do you think the data lies on low dimensional manifold images? Distributions are highly concentrated. We just saw that all the data is lying in small areas. Uniformly sampled points, supposing I went to that million dimensional space and I uniformly sampled all of it, and I start giving you samples, they look like static noise, never structured. They look like the static noise. So if I give you a random sample in a original input space, it's going to be it's going to look like this, a random image. A random image is going to look like that. And although non-zero probability of generating, you could have a face as a random example, right? I'm giving you a random point in that space. It's not going to come out looking like a nice flower or something like that. It's never observed. You don't get a random sample like that. Although there is a non-zero probability. It's one of those images, but it will not come out like that. Such a small probability. Text. If you generalize a document by a random, you generate a document by randomly generating text. Okay, you say, all right, monkey, you take this monkey and give it a keyboard and says, okay, start typing randomly. So it learns how to type the keys. Will it generate, a play of Shakespeare, right? A meaningful text, all right? That's a classic example that a monkey given a keyboard and infinite amount of time, will it generate Shakespeare, right? A poem. All right, so the natural language sequences occupy a small volume of the total space of sequences of letters. So the number of combinations that you need, that you can get out of a page of text is so large that natural language sequences, meaningful things are going to be extremely, extremely small. So it says, so the real data lies on a very, very small area of the space. And we refer to that particular area of that space as a manifold. This is called a manifold hypothesis. Data manifolds are smooth. Common theme of the example, they're somewhat smooth, meaning that there are no sharp spikes or edges. These manifolds are not like a sharp object, like a cube. Can the manifold be a cube, which has got a sharp edges in the corners? Probably not. There's going to be all smooth transitions going on these. The overall shape of manifold can be amorphous, uh, and they describe data sets that don't have rigid boundaries. So these are all some observations and hypotheses about the data sets. Manifolds traced by transformations. Manifolds can be traced by making small transformations. So here is a manifold structure of a data set of a human face. So they are now looking at the face in slightly different angles like this. You go from looking left all the way to the looking right. And I don't know what is this, looking at, upwards to looking downwards. So it's a combination of two dimensions, looking down and looking the other way. And this is a three-dimensional transformation of the human face as opposed to a two-dimensional. We're not simply rotating this image in two dimensions. It's a three-dimensional rotation. And we say all of these points in whatever space we have, image pixel space, trace a manifold, a set of points. Every one of them is a point in that space, and that is the manifold. So we now come to the concept called tangent distance. So we have now argued that the samples lie on a manifold. Let's say that this is a one-dimensional manifold in two-dimensional space here. And so we make some changes with the data that keeps moving along this, and person is looking left, looking right, and there is a certain point here. And we have an input point here, P, and we want to measure how far this is from this. Let's say it's a classification problem. There's one manifold here for dog, and there might be another manifold for cat, and we're saying which manifold is it closer to? This is a new one. Well, you could measure what's called the Euclidean distance between P and S. All right, Euclidean distance. We take differences between the values and square them and so on. Euclidean distance. Manifold distance, which is the shortest path between any point on the manifold and this, and saying instead of looking at S, we're just measuring how close it is to the dog manifold here. Or we can use this thing called tangent distance. That is for some data point, we draw a tangent to it, and we measure the distance of this tangent here. This is a right angle here, right? So this is the distance to this. So it's not distance to the manifold. It's not distance to a point, but it's distance to a tangent at that point. So we have three distances here. MD is manifold distance, ED is Euclidean distance, TD is tangent distance. And again, we're reminding ourselves, one of these points here on this line is, this is a two-dimensional case. The faces, this is a two-dimensional rotation. We are enlarging the face, the scale, and we are rotating the face. This is Y direction. It creates all of these images. And let's say somehow these images can be plotted in 2 dimensions. And so maybe it'll move along like this and turn around. And someone did a study of distance between, say, points S and P, and they're plotting here.
Professor,
Yeah.
there is a question.
Yeah.
Hi, Professor. I just wanted to get the clarification. What's the difference between the manifold distance and the Euclidean distance? Isn't the Euclidean distance the shortest distance?
Yeah, to a point. So we can measure the Euclidean distance to a point, right? So manifold distance is not to a point, but the manifold on which that point lies. So we are allowing for us to measure. Let's say we were dealing with P and S, but we are saying don't use S. S lies on some manifold. Tell me the closest point on the manifold, right? So the closest, maybe this distance P to this point here is shorter than to the point S over here, right? So we are replacing S by another point which is closer, because everything is there is a, let's say it's a dog manifold. Why go along with, we've somehow figured out that there is a manifold that dogs lie on. Although my data point may be S, this is a particular dog. We say, okay, no, we'll find another point close by, right? So manifold distance could be shorter than the, so it is saying, we're assuming that the data lies on a manifold. And for the classification problem, we want the distance to the manifold rather than distance to a given any given point. Instead of becoming a nearest neighbor classifier would say, well, if the nearest point is S, we classify it to as whatever this S is. That's what the nearest neighbor classifier says. So, you know, I'm going to have a manifold distance classifier, which says instead of using S, use for, if that's a prototype for that class, use this as the distance now, right? We could do the same thing for the other class too. What is the nearest point to that one? Well, use the manifold distance to that rather than the point as such, right? So one can design all kinds of classifiers where you measure manifold distance. But the manifold distance is not easy to compute. Euclidean distance is straightforward to compute. Right?
Exactly. So how do you compute the manifold distance then?
Yeah,
so
that is, we give up on it. We give up on it. And instead of that, we use tangent distance, right? Manifold distance, apparently, to do that is, so we'll get to that point. So we don't use the Euclidean distance to the points. We don't use the manifold distance. We use the tangent. The whole thing is labeled tangent distance is the way to do it. This is a plot of all these three. Tangent distance is the uppermost surface. The manifold distance is kind of close to it, which is below it. There is a light colored one, which is on top, which is tangent distance. There is a dark colored one below, which is the manifold distance. And there is a gray colored one below, which is this is a Euclidean distance here. Euclidean distance. This is manifold distance, a tangent distance. And they're plotting it on again this kind of space here, rotation and scale. So and they're measuring these three distances for, I think, taking a pair of points, a particular S and a P, and they're varying around on these samples. Maybe they did for every one of them to the original or something. Let's say this is the original point. Maybe this is the original point. And then you plot all the distances of all of these points, and that's going to trace some kind of a surface in this scale and rotation as you change these values. That value lies between 0 and 1. And so this is the nature. So we're going to have three different things here. It looks like quite often the Euclidean distance is small here. Maybe, yeah, it looks like what your hypothesis about Euclidean distance is small here. And maybe throughout it's looking small here compared to the manifold distance. And maybe the tangent distance seems to be a little bit higher than the, okay. Anyway, that's the nature of these things. But the important thing is, we are attaching importance to the manifold, not to the point. And so we want to use the manifold, but computing the manifold distance is not easy. So we do that with tangent distance, right? That's the sequence of thinking here. You can subject all of this to doubt and say, all right, I'm going to do this in a different way. Now let's talk about how do you, what do you mean by a tangent vector? So this is a simple way of doing nearest neighbor using the tangent vector. Patrice Simard described this long ago. He said, let's say there's an original image of a MNIST 6 image that we've got here. And he says, I compute from this original image X sub n, it's one of the samples I had. I compute from it a tangent vector to that. How do you get a tangent vector to that? Is it's a derivative. Remember, tangent is got to do with derivative. It is derivative of S of xn comma psi. So it is whose arguments are this xn. Its psi is the transformation you're going to be using. So the transformation is a rotation. Let's say we're rotating here. So this is a tangent vector corresponding to small clockwise rotation. So we take how much it changes when you subject it to clockwise rotation, and that is the derivative point here. So computer, how do you get that? Is approximation using finite differences. How derivatives are computed using finite differences. By subtracting original xn from the corresponding vector after transformation. Oh, okay. Transform it, and you get another image, and then you're going to have the derivative is going to be using a small value of psi and then dividing by psi. So that is dy by dx. How is derivative computed using finite approximation, that kind of thing. So you get the tangent vector here. That's the tangent vector to this. And you take a small contribution, you take the original image, add to this the tangent vector, multiplied by an epsilon, like earlier on we saw in adversarial training, and you create a new image. So this one is adding a small contribution to the tangent vector. So this image looks similar to it, but slightly different from it. And it's based on a true rotation transformation. And they're just comparing it. Supposing you said, I'm going to regularize my classifier by using data augmentation, by taking my original data, keep rotating it, and I'll get new images. Supposing I took my original image and rotated it by the same thing you're doing here, it says, well, that image looks like this. Oh, okay, that looks quite similar to what we got out of this, but it's not exactly the same thing. So the tangent vector is maybe similar to data augmentation, but it's different from it. So the tangent distance classifier. So now we can build a tangent distance classifier. Tangent distance is used to build invariance properties into distance-based methods such as nearest neighbor classifiers. So you want your classifier to be more robust than a standard nearest neighbor classifier. And the distance between point X and manifold is computationally difficult. Okay, that's the point I made earlier in answer to your question, that couldn't you just go and calculate the distance to the manifold rather than the tangent? He says this would require solving an optimization problem. So what is the manifold? It would involve all the other points that you have in your data set, and that might be a large number. To figure out what your coffee cup manifold would look like might be complicated. And the cheap alternative is to use distance between point and the tangent plane, by solving a linear system of the dimension of the manifold. So this says, we just intuitively talked about it, but it may involve something more, solving a linear system, the dimension of the manifold. So again, tangent distance classifier. It says, okay, instead of looking at the distance between point X, point to the closest point X, you look at the tangents between the points in the data set. So that is the tangent distance classifier. It's been around for a long time, but people didn't use it a lot. I'm talking about 30 years ago. Computers were not so fast as they are today. People said, this is too complicated. Maybe there are better methods of regularization than tangent distance. So it didn't pick up much steam, but it was very nicely based on proper formulation of the problem. Tangent propagation is another method where it becomes a true method of regularization. It is related to tangent distance, but it trains a classifier with an extra penalty. So it says, I'm going to give another penalty term. Makes each output f of x of the neural network locally invariant to known factors of variation. So it says the output should be invariant, saying it shouldn't change just because you have some factor of variation on the input. These factors of variation correspond to movement along the manifold near which examples of the same class concentrate. So the data is getting concentrated here. And so the factors of variation. So if it is all moving in that same area, the output shouldn't change dramatically. So the tangent propagation tangent prop regularization. It says the local invariance that we just talked about is achieved by requiring the derivative of x. This is the vector of f of x, right? F is the function of x to be orthogonal. So this is, we're talking about the manifold here, to be orthogonal to the known manifold tangent vectors vi at x. So this is the manifolds here. There's a x1, x2 is the two-dimensional space. There's a green manifold, there's a blue manifold, and there's a tangent over here being drawn here, and the normal to the tangent being drawn. We are saying that the local invariance is achieved by requiring the derivative to be that, which is a tangent, to be orthogonal to the manifold tangent vectors at v sub I. So there is some orthogonality requirement going on here. Equivalently, that the directional derivative of f at x in the direction of vi be small by adding a regularization penalty. So this is saying there is going to be a penalty term which is taking the derivative of f of x multiplied by this vector v here, right, which is a manifold tangent vector. This is the manifold tangent vector. And so we add this term here, normal to that, and that is the regularization term. Let's see if the next slide tells us a little bit more. What's going on here, another view of it, we are looking at it in the one-dimensional manifold case. X1, X2 are two dimensions of the input data. The data are all lying on a line here. This is a manifold M. There's a point Xn over here. Psi is the name of the transformation. So this is, they put an arrow here. That is, when you take the image and you start rotating, and psi would be the rotation transformation. The data keeps moving along like this in this X1, X2 space. And at a particular point, it's tau n here. So we saw that in the previous diagram, I think, which is kind of repeated over here again. And two-dimensional input space showing effect of continuous transformation with a single parameter psi. Let the vector resulting from acting on xn by this transformation be denoted by s of xn psi. Right? So we get a new vector defined so that s of x0 equal to x. So when you don't make any transformation, you write the point. The tangent to the curve M is given by the directional derivative tau is equal to, delta S, right? ds by d psi. So this is a function S here. We're taking the derivative of that. The tangent to vector at point xn is given by this derivative here. All right, that's this quantity we just saw. All right, so that is tau n is being calculated here. And that is the tau n. All right, so that's, yeah, there was no tau n used in this slide, maybe earlier. Okay, fine. So that's, this is the kind of thing that's going on here. So regularization to encourage invariance transformations by technique of tangent propagation. Consider the effect of input transformation on input xn. A 1D continuous transformation parameterized by psi applied to xn sweeps a manifold M in d-dimensional input space. And we compute a tangent vector to it. And the story continues here that under a transformation of input vector, the network output vector will change derivative of output k. Let's say we kth output of the neural network. That is the derivative output k with respect to psi. How does that output yk change with respect to psi? The transformation is being computed over all the dimensions of the space, I equal to 1 through d. And you have dy, k, dxi. Oh, this looks like a chain rule of calculus. It is computing dy by d psi by dyk by dx and dxi by d psi by chain rule of calculus. That is written as jki tau I, where jki is the ki element of the Jacobian matrix J. So we're bringing the first derivative matrix Jacobian here. And tau I is the tangent vector. Well, what does all this mean? Result used to modify standard error function. So instead of using the loss function E tilde equal to E plus, we take the original E, whatever it is, the regularized E, lambda omega, where lambda is a regularization coefficient and omega summed over all the samples here. And I suppose these are the transformations here. And we got this derivative term, and the derivative term is being expanded by this thing here. Wow, it becomes a computable thing here. So we have to deal with Jacobians and the transformations and over all the dimensions that becomes this omega to encourage local invariance in neighborhoods of data point. So what has happened here is somehow this idea of the tangent becomes an additional penalty term where the method of supervised classifier is able to deal with these rotations and so on using that same idea of tangent incorporated as a regularization term. So it's pretty beautiful mathematics that they brought it to this stage. And the tangent prop implementation, as with tangent distance, tangent vectors are derived a priori. You take your data set and you create tangents from them. From the formal knowledge of the effect of transformations such as translation, rotation, and scaling of images. And tangent prop has been used for supervised learning, reinforcement learning. Some of these guys in reinforcement learning said, hey, we could use that. We got things rotating all over the place and the robot is moving around and we know the transformations that are going to be encountered, rotation, translation, and so on, but not squeezing and more complicated things maybe. And then final thing is manifold tangent classifier. Eliminates the need to know tangent vectors a priori. It doesn't say take all your data set and create a tangent version of it. Uses autoencoders to estimate manifold tangent vectors. Autoencoders play a role here. We haven't covered the topic yet. Autoencoders take an input and produce itself as output and along the way compress it. So autoencoder reproduces it. So that's why it's called autoencoder. But what is the use of it is it creates some representation, which is kind of smaller than the full input and the full output. And so it's a nice description of the object is what an autoencoder could do for you. Uses autoencoders to estimate manifold tangent vectors. Goes beyond classical invariants that arise from image geometry. Translation, rotation, scaling are only some geometrical transformations. And we can also include factors that are object specific, such as moving body parts. I'd like to work with the arm of the robot or the leg of the robot and so on. And there's an example coming up. So this comes in as a topic in a much later section of our study of deep learning. It comes under, I think, autoencoders. Here is an input image of a dog, I think. And they said in standard method of tangent vectors, these are tangent vectors, you create new images along maybe different transformations or different degree of transformations. You're getting all these, the tangents don't look very, very nice. We may have to add it to give other training samples. This is just the tangent vectors. These are the tangents to this. And it was using local PCA, no sharing across regions, some method to generate these tangent vectors in a lower dimensional space, PCA. But a version of autoencoder called a contractive autoencoder, which is a more sophisticated way, it is doing transformations, may not be user specified. It is saying these are all the transformations that are possible with the data. And so we have got to see how an autoencoder is trained to do that. That's a different topic. All right, so those are the 4 methods of regularization. One was tangent, other than adversarial training. Earlier on, it was about the first of these methods here on tangent distance method and tangent propagation method and manifold distance method. This last topic, I just threw it in because it keeps coming up again and again. It's not a method of regularization, it's just manifold learning. An important idea underlying many ideas in machine learning is manifold learning. Learning what the manifold is. The manifold is a connected region. The object is connected up. It's not like different parts. Mathematically, it's a set of points in a neighborhood. It appears to be in a Euclidean space. Example, we experience the world as a 2D plane while it's a spherical manifold in 3D space. Yeah, we experience the world as a 2D plane. We are walking around, not, I guess we were climbing a mountain, it's not a 2D plane, it can be 3D. While it is a spherical manifold in 3D. Yeah, the manifold we are on, the Earth, is actually 3-dimensional, right? It's actually a sphere. We are on top of a sphere when we're walking around, outside the house. But we experience it as a 2D plane. Although locally, it's a 2D plane, but globally, it is we are on a sphere. So it's a connected region in a lower dimensional space. And although manifold is mathematically defined, in machine learning, it is loosely defined. Okay, so we kind of give ourselves some leeway. A connected set of points that can be approximated well by considering only a small number of degrees of freedom embedded in a higher dimensional space. That is how we define a manifold. A mathematician who's a topologist might say, hey, that's not how we define a manifold. All right. Training data lying near a 1D manifold in 2D space. This is a 2D space and you have training data. It's going along and long and long like this. It's all. So we say this lies on a 1-dimensional manifold. Although it's on 2-dimensional data, it is lying on a 1D space, 1-dimensional manifold. The solid line indicates the underlying manifold that the learner should infer. The learner should only infer this manifold. So it is inferred dogs are this manifold, cats are this manifold. So we are not dealing with the original data space of X's. We are dealing with the distance between any point to the manifold. In machine learning, we allow the dimensionality of the manifold to vary from one point to the other. This often happens when the manifold intersects itself, as in figure 8. So you might have, the dimensionality can vary. Okay, anyway, that's some fine point here. Manifold learning surmounts Rn. So the problem, Rn is n-dimensional space. It is sometimes hopeless to learn functions with variations across all of Rn. That is all n dimensions. Manifold learning algorithms surmount this obstacle by assuming most of Rn consists of invalid inputs. Most of the text you have is garbage, or most of the images you have is garbage. And that intersecting inputs occur only along the manifold. So introduced for continuous data and in unsupervised learning, the probability concentration idea can be generalized to discrete and unsupervised settings. All right, so it's a very, very important topic for the future of machine learning. Last slide here, manifolds discovered for human faces. So we saw those this is on images that have been rotated, and they're also on emotion, right? Person is maybe unhappy in the beginning and gets neutral and is very happy at the bottom here. And we're also rotating left to right, right? The face is going from looking right to looking left. Variational autoencoder, a particular method. Mihir, who's here today, that's his area, is that work of variational autoencoders. And it discovers underlying two-dimensional coordinate system. It says, it discovers the manifolds for these kinds of things. I mean, there's some papers written on this saying, what is the manifold? Anyway, it's an exciting topic on coming up. All right, so that's it for today. And maybe that's exactly the right amount of time for Mohammed. Tell me, what do you plan to do today in the breakout? Do you have a breakout today?
So yeah, probably I can, go over a little bit on how to create a generative adversarial network.
Oh, you're going to launch off into that deep end, huh? Okay.
So you
I've just
already
said
covered up a bit of GAN today, right? So I can just,
one slide of GAN, but I said it's not the same thing. But anyway, GAN is an important topic. I'm glad you will talk about it, because some of the students already want to do a GAN project. And by the time I get to GAN, it's going to be end of the semester as usual. You might as well tell them what a GAN is.
Yeah, I'll just give a brief insight about it.
Fine. That's fine. Yeah. And students, you all don't need to jump to only the same topic of GAN. I can do all kinds of interesting things like I described. As I'm going along, I'm suggesting small topics. I'd be more excited if you learned about one small topic and told me about your discoveries on that topic, rather than saying one more GAN to generate some more faces or celebrity faces or something. I've actually seen literally hundreds of projects on those kinds of topics. So I'd like you to be more creative than that. But anyway, the limited amount of time, you can define a limited project. But anyway, GAN is fine, and that's good. All right, and I will start with optimization next week. I keep on debating every week what should be the next topic. And I said, that's the next logical topic is optimization. If I skip any of these things, I run into trouble because we haven't talked about it, and we need that. Optimization is is a workhorse of all of deep learning. So we need to know what's the difference between Atom Optimizer and ADA Prop and whatnot. So we'll talk about that. Okay.